Okay, good morning, everybody. This is Unit 7, Cartesian Vectors. We'll do the first day today, Introduction to Cartesian Vectors, add, subtract, multiply, magnitude, and direction. Okay, and so what we'll do is put a comma right there. Now, this is what we're going to look at. This is the sort of the plan for the unit. If you kind of take a look at this, you got 1, 2, 3, 4, 5, 6, about 6 videos here. Then we'll take a few days to review, start scheduling tests. All right, so in the last section, we studied geometric vectors. Now we move to the Cartesian style. Note that both styles still represent that same idea, a magnitude and a direction. Geometric vectors are good. Geocentric. No, this is supposed to be geometric. There we go. Geometric vectors are good for an introduction idea, in an introductory into the idea of what a vector is, because the direction and the magnitude are very apparent, right? So they're just sitting right there in front of you. That was what we studied in the previous chapter. But we will soon discover that they're actually less versatile algebraically and in terms of like actually just working with them than the Cartesian vector, right? Some pros and cons of the Cartesian vectors are, well, they're easy to add and subtract. They're easy to multiply, and they work in 3 dimensions or even 4 dimensions. And there's no cons, actually. They're all pros. And so we will begin in 2-dimensional vectors and add the dimensions later on. So by the 3rd day, we're going to work in 3 dimensions. First 2 days, we'll just stick with 2 dimensions. And then as the 3rd dimension appears, you'll kind of already be reasonably familiar with it. So there are 3 ways to represent a Cartesian vector. Here, okay? 3 ways. Let me put a little bit of space. There we go. All right, so the first way is graphically. And then the next way would be the unit vector. And the next way would be the square bracket. Okay. So I'll go through and explain these guys. So graphically, let's say I've got some vector, okay? And boom, there it is. And we'll call it vector A. And basically, each of these vectors, it has sort of like an A1 component and an A2 component. Our textbook is going to use A1 and A2 for the X and the Y, right? Some would use A sub X and A sub Y, but our textbook happens to use 1s and 2s, okay? So I'm just kind of sticking with what our textbook deals with, all right? So this would be the A2 component and the A1 component. The component would just mean sort of the direction, how much the vector has in a particular direction, okay? Then there's also now the unit vector, right? So let's represent this A vector. Oh, no, this is the square bracket. Sorry. Let me erase that. So this A vector could be represented by A1 times some vector I plus A2 times some vector J. And we'll go ahead and explain what I and J are. Those are unit vectors in the X direction and unit vector in the Y direction, okay? And so let me go and tell you the square bracket way. So the square bracket is I can actually just write A1 and A2 with square brackets here. Okay, let me make this a little bit bigger. So A1, and then I'm going to write comma A2, right? And you know this is different than a point, because a point would have sort of maybe like X1 and Y1. This would be a point. This is a vector here, if you have the square brackets, all right? So let's actually make some numbers here. So let's say that this happened to be 2 and this happens to be 3. Well, in our example here, our vector A would be 2I plus 3J. All right. Let me make that a little nicer for you. I plus 3J. And basically, what this means is it's like go 2 in the X direction. That's what this says. And go 3 in the Y direction. And I don't know why they introduced new letters for this, but they did. For some reason, I always felt like they should just put an X with a vector symbol on top of it and a Y with a vector symbol on top of it. But whatever, they decided to do it differently. And so now this would be our vector 2, 3, right? And so each of these green vectors are the actual sort of written, they represent our specific vector in this specific example, vector A. Each of these pink vectors here, these are sort of like your generic definition of what a vector would be, okay? And that's kind of the idea, right, for these things. So as these vectors start to unfold and we draw them in the next examples, you'll start to see how they work, okay? So some operations with Cartesian vectors. So now in these next examples, everything we're going to be doing, okay, is going to be with mostly Cartesian vectors, but we'll have some geometric vectors sort of flipping in, right? Slipping in. So how do we find the magnitude of a vector? Okay. In the geometric vectors, let's say I've got a vector here. This is a geometric vector, which was the last chapter, right? So let's say I've got some vector and it's called 7 at 200 degrees, okay? Well, what's the magnitude of that vector? The magnitude of this vector is just 7. So how do you find the magnitude? Well, it's just sitting right there, okay? So now then the question is, well, how do I find the magnitude of one of these geometric vectors here? Well, as it turns out, you'll notice that this is a Pythagorean sort of triangle here, a right triangle. And what I can do is I can take this side, which is 3, and that side, which is 2, and I can use the Pythagorean theorem to find the length of the hypotenuse, and I've got the magnitude of my vector that way, okay? And so, as it turns out, you're going to use the magnitude of a vector. We're going to use the Pythagorean theorem. And so I'll write that down for us. So the vector's magnitude is equal to the square root of its x component squared plus its y component squared. And so for our green vector above, which was called vector A, its magnitude is the square root of 2 squared plus 3 squared, which would be the root of 15. If I got that right. 14. No, 13. 13. Okay. So that's how long this vector is up here, this vector A. Okay. Well, how would I find its direction? Remember, the direction of this vector is, you can represent it with some kind of angle in trig bearing, maybe, right? Or you could represent it in true bearing, or quadrant bearing. I'm going to generally stick with trig bearing because it's one of my preferred ones. And so, excuse me. Sorry. So how do we find the direction of this vector? Well, we're again going to exploit the fact that it's a right triangle. Okay, and remember that's a 3 and that's a 2. So to find its direction, it's just the tangent inverse of the y component over the x component. And that would give you your direction. All right, and that's going to be in trig bearing. Okay, I should have written that in pink because this is sort of the general rule. And then in green, I want to write our example. So the general rule is you do the tangent inverse of the y component over the x component, and this would give you the direction in trig. And don't forget to add 180 degrees if the a or the x direction is negative. Okay. Now, for our example, here we're going to do tangent inverse of the y component over the x component, or the tangent inverse of 1.5. And I should have this memorized by now, but I don't. And so it's just the tangent inverse of 1.5 is about 56 degrees. So that's how much that would be. Okay. So that's that. Well, what happens if you have two vectors and you want to add them? There's these these Cartesians, right? So let's say I've got a vector A, and it's A1, comma, A2, and I've got a vector B that's B1 and B2. What happens? What is A plus B? Well, it's a new vector. And I basically just take A1 and I add B1. And then I take A2 and I add B2. So let's do that with an example here. So let's say I've got a vector A. That's 2, 3 from above. Now I'm going to introduce a new vector B. Let's call that negative 1, 4. And now I'm going to say, what is A plus B? Well, it's basically just equal to 2 plus a negative 1, comma, 3 plus 4. And so the resulting vector is going to be 1, comma, 7. So this is a new vector, 1, 7, which is equal to the sum of the vector A plus the vector B. Remember, if you take a vector and you add another vector, the result is a new vector. Remember, we learned that. So if I take a vector and then I add another vector here, the result would be a new vector. Okay, and that's kind of the idea. So in our example here, here's our, here's our one vector, right? Here's our second vector, and we added them for a new vector there. All right. How do we take a vector A, for example, and multiply it with a scalar? Okay. So let's say we've got our vector A. It's A1, comma, A2. Right. I always get these square brackets messed up. I always make them too small. A doesn't quite fit in there. So, and let's say I've got some vector or some scalar K. All right. So what would Ka look like, right? Well, as it turns out, it would just be K times A1, A2, which is you're gonna be able to distribute this k. So it's actually going to be k a1 comma k a2, right? Hey, there you go. So let's make up an example. Let's say that our a vector is again 2, 3. Okay. And let's figure out what is equal to negative 3a. Negative 3a is just negative 3 times 2 comma 3, which is negative 6 comma negative 9. So that would be a new vector, negative 6, negative 9. I'm actually going to draw this one out for us, right? So remember, our first vector was 1, 2, comma 3. So 1, 2, and then 1, 2, 3. This was our a vector. And if I multiply it by a negative 3, it's going to tell me that it's the new vector, negative 6, negative 9. Oh, negative 6, negative 9 is, 1. Sorry. Let me do this. So 1, 2, 3, 4, 5, 6, and negative 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it would be, I guess, this vector, right? And this is negative 3a. Oh, look, that actually makes sense because it appears to be 1, 2, 3 times larger than a and in the opposite direction, which makes sense based on what we previously learned about multiplying vectors and scalars. Remember, all it does is it changes the direction, right, of the vector if it's negative, and it could alter the magnitude as well, right? So we saw that there. Okay, that's great. Okay, here's another little operation that's helpful. It's finding the vector between 2 points. Okay, so remember what points are. I'm gonna have 2 points here. In this unit, basically, a point would be, x1, y1, and then another point could be x2, y2, right? And when you do points, oftentimes you assign capital letters with those things, okay? Now, oftentimes you want to find vector a, b, right? Well, it's actually going to be a vector, and we could write this in Cartesian form. And in order to find it, you basically just do x2 minus x1 and y2 minus y1, all right? So that's our vector there, okay? And I'm going to go ahead and give us an example, right? So maybe I'll do it here. And I'm going to say, let's say we've got some point, which is 1, comma 2, and some other point B, which is maybe 4, comma negative 2. What is vector AB? Okay. Vector AB is, according to this rule over here, it's 4 minus 1, comma, negative 2 minus 2, right? Which would just be 3, comma, negative 4. Interesting. Well, let's actually draw a picture of this, all right? Let me get an orange here. All right, so we're going to draw a picture of what we just did there, okay? Okay, so let's see, how much room am I going to need? I'm going to need about 4, negative 2, and 2, 1. Okay, so maybe I'll need something like this. So 1, 2, 3, 4, and negative 2, and then 2, 1. So point A is here, 2, 1. And point B is here, 4, -2. The vector AB, would be this vector here, right? Which basically means it's, let's see, oh, wait, I messed this up. Hang on. It's not 2, 1, it's 1, 2. I flipped these guys. So it's 1, 2. So A is in the wrong spot. Let me put A in the right spot here. Let's see, it's 1, 2. There's A. 1, 2. I'm always getting this stuff wrong. Okay, now we go. There's AB. Okay. So what does this basically mean? This means vector AB is a vector that tells you to go 3 in the x direction and 4 in the negative y direction. So 1, 2, there's our 3 in the x direction. And then 1, 2, 3, 4. So it's 3, -4. That's what vector AB is, okay? And it has a magnitude and a direction. And remember, its location is not part of its definition, so it doesn't matter where it is. I can make an equivalent vector right here, which would be the same vector, right? AB. It would be equal to vector AB. So that's the introduction to Cartesian vectors. What we're trying to get ourselves accustomed to is using this new square bracket idea, and how that the Cartesian vector is really just a vector that focuses on the x and the y components of a vector. All right? And so for the first section, you're going to be practicing finding directions and magnitudes, adding and subtracting, and things like that. Tomorrow, or the next note, we'll talk about what the dot product is. Okay?